Hello everyone, in this video I will introduce our paper JOLO-GCN, Mining Joint-Centered Lightweight Information for Skeleton-Based Action Recognition. Here is an overview for skeleton-based action recognition. According to the input information, we roughly divide skeleton-based action recognition into two categories, single modal method and multiple modal methods. Here is the motivation of our method. There are two obvious disadvantages in recognizing human action relying solely on skeleton sequences. Firstly, for action categories, many categorized by local subtle movement, the difference between the skeleton extracted from successive frames are so subtle that it is hardly useful for describing such actions. Secondly, skeleton alone might not be as distinctive in describing certain action categories. Multiple modal methods takes up more resources. As the complexity of the input increases, the number of network parameters and the computing resource consumption increase substantially compared to the single modal counterpart. To move beyond the limitation discussed above, we have some ideas. Firstly, skeleton information provides global motion of the body joint, and more local subtle motion information should be introduced to improve the modeling of body motion. Secondly, the introduced local motion information should be lightweight, which ensures that the model complexity keeping relatively low. So, we propose to augment the skeleton with the lightweight local visual information surrounding skeleton show joint in the form of joint-aligned optical flow patches. And we propose a two-string GCN architecture, JOLO-GCN, to fuse local motion information from a JFP sequence with global motion information from a skeleton sequence. For getting the JFP, firstly, we apply the 2D pose estimation on the image sequence and augment the 2D pose skeleton. Then, we treat human joint coordinate as the anchor point in the image and crop out joint-centered appearance patch JAP. The JAP is lightweight because redundant background information has been removed during this process. Finally, we estimate the optical flow between successive JAP pairs of each body joint for augment the JFP. After center aligning the JAP pairs, the global displacement of the joint is actually eliminated. Therefore, JFP provides only local subtle motion cues. This is the framework of the JOLO-GCN. It is a two-stream GCN-based network architecture which processing the skeleton sequence and the JFP sequence independently, and we train two branches independently. The predicted score from these two branches are merged into the final predicted score for each action class by linear blending. The proposed JOLO-GCN is built and evaluated over two different GCN-based backbones, ST-GCN and 2SA-GCN. We evaluate our method on three large-scale human action recognition datasets, NTU-RGBD, NTU-RGBD 120, and kinetic skeleton dataset. And our method augments the state-of-the-art results on these datasets. To appreciate the accuracy gain by including the JFP string in more depth, we compare the performance of different branches on every action category. Compared with the baseline method, our method has gained significant accuracy improvements for these actions mainly characterized by local subtle movements. To find out whether other patch modality can possibly be better options over JFP, we conduct a series of experiments to evaluate different patch modality and their combination with the input skeleton string. Among these different patch modality, JFP performed best. That's all. Thanks for your attention.